In this video, we're going to talk about free undamped motion. This is an application of solving linear second-order differential equations. So suppose that you have a body, so some object of mass m attached to one end of a spring. So here's the wall, and you have some spring, and you have some object of mass m attached to it. And let's say that at this point here, the way I drew it, this is at the equilibrium point. So you can either pull the object that way to the right. Let's make that direction positive. So this direction it's positive, or you can push the object against the spring in the other direction. And let's say that you move it to a distance x away. So if x is positive, x is positive when the string is stretched, and x is negative when the string is compressed. The spring is compressed. So there's a physical law called Hooke's law. And Hooke's law says that when you push or pull this object, there's a restorative force that the spring exerts on the mass. And this restorative force, let's call it F sub S, S for the spring, is in the opposite direction of the direction in which you're moving the object. And it's proportional to x. So it's negative kx for some positive constant k. And the constant k is called the spring constant. So that is the force acting on the mass, this F sub s. And by Newton's law, or one of Newton's laws, this force, negative kx, is the mass times the acceleration of the object, ma. Well, the acceleration is the second derivative of the position, so negative kx equals mx double prime, and then we can just add kx to both sides to get mx double prime plus kx equals 0. Okay. And this is a second order differential equation with constant coefficients. And when you have this setup, it's called free undamped motion. So in this case, the coefficient of x prime is 0. Okay, that is the undamped case, and the free case is when the constant on the right is 0, or the function on the right is 0. So in general, you could have mx double prime plus kx, so that would be undamped motion equals some function of time. And then that would be forced, not free. So this is the easiest case, free undamped motion, and we know how to solve this differential equation. And when you solve this differential equation, the solution of this differential equation is x of t equals a cosine the square root of k over m t plus b times sine square root of k over mt. And we can use the notation omega naught, omega 0, to be the square root of k over m. So then x of t would just be a cosine omega naught t plus b sine omega naught t. Okay. So the question is, what does that look like? Well, oh, by the way, the capital A and capital B. So here, capital A and capital B are just any constants because I didn't specify any initial conditions. But once you specify initial conditions, then you'll be able to solve for constants A and B. Okay, so going back to this, we want to know what the graph of this looks like. Now we know how to graph each of these terms separately. So you know how to graph A cosine omega naught t. Right? That's just, you take cosine and then you stretch it by a factor of a vertically, and then there's a horizontal compression or stretch by a factor of omega naught. And similarly for b sine omega naught t. That's just the sine function stretched vertically by a factor of b and then compressed horizontally by a factor of omega naught. But the question is, what happens when you add them? So each of the individual terms is a wave. But when you add them and then graph that, what do you get? Well, it turns out that we can do some algebra to rewrite this. So first, define c to be the square root of a squared plus b squared. Okay. Then, if you look at a over c squared plus b over c squared, you get a squared plus b squared over c squared. And by definition of c, this is equal to 1. So basically, whatever your a and b are, the point a over c, b over c is on the unit circle. So what that means is that we can write this as cosine theta sine theta for some theta. This point a over c, b over c. Or we can, the notation we'll use is alpha. Okay, right? So since this point is on the unit circle, so there is some number alpha between 0 and 2 pi such that a over c, b over c is equal to cosine alpha sine alpha. So let's just draw a little picture. So your alpha doesn't necessarily have to be between 0 and pi over 2 because your a and your b might be negative. So let's say this point was your a over c, b over c. Then alpha would be that angle. Okay, that would be alpha. So alpha is somewhere between 0 and 2 pi. Okay, now using c and alpha, we can rewrite x of t above. So first I'm going to divide and multiply both sides by c. So we have x of t equals c times a over c, capital C, cosine omega naught t plus b over c sine omega naught t. And a over c is cosine alpha, b over c is sine alpha. So this is c times cosine alpha cosine omega naught t plus sine alpha sine omega naught t. And by the way, this omega naught t is in parentheses. There's implied parentheses here. So it's not sine of omega times t, it's sine of the quantity omega naught t. And the same with cosine. But generally speaking, it's often, the parentheses are often left out. Okay. Now here we have cosine alpha, cosine, say beta, plus sine alpha, sine beta, where beta is omega naught t. There's a trig identity for this. So there's this trig identity that implies that this is the same as c times cosine of omega naught t minus alpha. So that is x of t. Well, recall that from your pre-calculus or trigonometry class that this is just a cosine except stretched and shifted and compressed. So let's review how that works. So first, you start off with the function cosine t. So let's say f of t is cosine t. So hopefully when you learn pre-calculus, you learned a bunch of steps to get from cosine t to something like c cosine omega naught t minus alpha. And how does that work? Well, the way I do it, that I think is the best way to do it, is to start with this function and then see what steps you have to do to get each next kind of component of your function. So for instance, for this capital C, I can define a new function g of t to be c times f of t. So that would be capital C times cosine t. So I start off with my f of t, and then I define a new function g in terms of f. I just multiply f by c. So what that does is a vertical stretch or compression by a factor of c. Okay, then the next step from g of t to say h of t is I define h of t to be g of t minus alpha. So that's going to be c times cosine of t minus alpha, right? If I replace t by t minus alpha. So what that does is it shifts the function g to the left or to the right, depending on whether alpha is positive or negative. So this is a horizontal shift. And then the last step to get, say, j of t is I replace t by omega naught t. So it's h of omega naught t. That's going to be c cosine omega naught t minus alpha. And so h of omega naught t compared to h of t, that's a horizontal stretch or compression depending on whether omega naught is less than 1 or greater than 1. Okay? So basically it's a wave. It's a wave. And this constant c, that's the largest value of x, right? Because cosine is between -1 and 1. So this function x of t goes up and down between c and -c. It's c when cosine of the inside is 1, and it's -c when cosine of the inside is -1. So x of t bounces back between c and -c. And so c is called the amplitude of the function of the wave. And the period is the time required for the system to complete one full oscillation. Well, that would be, say, capital T equals 2 pi over omega naught, right? Because without the omega naught, if it was just cosine of t minus alpha, then it would take 2 pi, but then when you have this omega naught t, then the time it takes gets divided by omega naught. Okay, so let's say that, I mean, the units of time depend, but let's say that this was in seconds, right? Then, so that would be the period, and then the frequency would be how quickly it cycles. Well, so the shorter the period, the higher the frequency. And the period and the frequency are inversely related. The frequency is 1 over t. So that's omega naught over 2 pi. And so the units of this is cycles per second, if we're using seconds as units of time. And cycles per second, the units of that is called hertz, Hz. Okay. Also, this constant alpha here is called the phase angle. So that's alpha. All right, so basically what happens with the spring is what you would expect from your intuition, that when you have a frictionless surface, okay, and you pull the block back, it's just going to swing back and forth. Back and forth across the equilibrium position between C and negative C, some constant, forever. And how far is it, what is C equal to? Well, it depends on your initial conditions. It depends on your x of 0. And it also depends on your initial velocity, x prime of 0. Okay, so this is a neat application of second order differential equations. This is the simplest case, this free undamped motion, but we will also see what happens when you have external forces and damping.